Hi, Year 12. Here's, fortunately for you, the last statistical test that we need to have a look at. This is the chi-squared test. That's not chi or chi, it's the chi-squared test. This is the, as I said, the last statistical test that you need to be familiar with. So we're going to have a look, again, follow the same process we've done before. We'll look at the kind of the process that we go through, why we use this particular statistical test. But we really want to focus on the interpretation of the result at the end. I always think it's worthwhile knowing how you got to that particular result to interpret. So we'll take you through the whole process. But the first thing is to think more carefully about any statistical test and how we'd carry them out. So what I'd like you to do is to have a think about, from the lessons we've had before on student t-test and Spearman's rank, correlation coefficient, what particular steps should we go through when we carry out any statistical test. So you pause the screen now and just have a think about what are the key things we should always do with any statistical test. Pause now. Okay, hopefully you've managed to jot down a few ideas. So the key things we always need to think about and we always need to go through. The first one, hopefully you're confident with this by now, is stating our null hypothesis. Once we have our null hypothesis, we can then kind of get to a point where we can either accept that or reject that null hypothesis. So that's our first step. Then we're looking at why we're carrying out a particular statistical test. What reasons do we want to do it, and why is it appropriate? For this particular example, we're looking at the chi-squared test, and it's particularly good for looking at frequencies. Okay, so quite simply, we're counting. How often does something occur? Next thing to do is what level of significance. We've always gone for that 5% level of significance, so less than 5 times out of 100 would the particular event that we're investigating have occurred by chance. Okay, so it's highly unlikely to have occurred by chance. Doesn't mean that it hasn't, but less likely than more likely. Next thing to include is calculations, what steps do you have to go through, and then finally interpret that particular test statistic and accept or reject our null hypothesis. Okay, so a number of steps that we always need to go through. So let's have a look at an example. The example we're going to have a look at is a genetics example. So I'm kind of taking you back to year 11 GCSE, and we're going to see if a set of results that we're going to observe and see from a particular test cross, how they compare to an expected set of results. Now this is a particular statistical test that is regularly used for genetics because we have expected ratios. We expect to see a particular pattern of results in a genetic cross, so we can look at the results that we actually observe, do they fit with our expected, our predicted pattern of results. That's why this particular test is really, really useful. Okay, so just a reminder, this is our Punnett square example, and we're going to look at the outcome of a genetic cross between two heterozygous individuals. So heterozygous means the individual has two different alleles for a particular characteristic. So in this case, we're using the classic donation, we're using a capital letter and a lowercase letter to represent a dominant and recessive allele. So across the top here of our Punnett square, we've got a dominant allele represented by the capital R, the recessive allele represented by a lowercase r, and we've got the same for the other individual. So what I'd like you to do now is to pause the screen and just work out what the combinations would be, and then tell me what the ratio would be for those particular combinations. So if you pause now. Okay, so if we go through and we look at, we've got the dominant R allele in this location. If through a fertilization process those two particular alleles come together, we would end up with an individual that is homozygous dominant. So it's got two alleles that are the same. Okay, so it's got 4 possible combinations. One of those combinations is homozygous dominant. We've then got a situation where we could have an individual that's heterozygous, just as the parents were. We have another individual that's also heterozygous, so we've got 2 out of the 4 possibilities, or 50% of the outcome we would expect to be heterozygous. And finally, we've got 1/4, 1 out of the 4 available combinations would be homozygous recessive. So thinking about what the expected ratio would be, that should be fairly straightforward. We would expect a 1 to 2 to 1 ratio when we're looking at the individual genotypes from that particular genetic cross, a 1 to 2 to 1 ratio. So if we kind of work through from that and look at that particular ratio, that particular pattern, that 1 to 2 to 1, Fairly classic relationship. You often see it as a 3-to-1. If we were looking at the phenotype, what could we physically see? Because we've got these dominant alleles, but we're looking at the genotype. So I've got a 1 to 2-to-1 ratio from the genotype. So if we had a sample size of, say, 40, we should be able to use that expected ratio to kind of come up with a figure of the number of expected individuals, how many individuals out of that sample size of 40 would we expect to be homozygous dominant, how many would we expect to be heterozygous, and how many would we expect to be homozygous recessive. So we've got 4 possible combinations, 1 to 2-to-1, so 4 different combinations. 1/4 of that sample size we would expect to be homozygous dominant, 1/4 we would expect to be homozygous recessive, and 50% of that population would expect to be heterozygous. So for a sample size of 40, we would anticipate our expected results would be 10 to 20 to 10. So it's quite easy to determine the expected results, particularly in a genetic cross, because we're looking at the particular ratio and we're just dividing up our sample size in that particular ratio. Okay, so 10 to 20 to 10. So what about our observed results? So the whole purpose of this particular statistical test is to compare our observed results with our expected and trying to come up with are they different enough to warrant kind of further investigation? Do they look kind of far away from that expected pattern? So here's a set of results. That's what you think, is this particular, does it fit the pattern? So there's a particular pattern, 11 to 19 to 10, follows a very similar pattern. You know, how far away are those for us to be kind of thinking, is there something affecting that particular outcome? Okay, 11 to 19 to 10. Looks pretty close to 10 to 20 to 10. Next sample, 12 to 19 to 9. Again, very similar kind of pattern. And finally, 10 to 16 to 14. They're all following a pattern where that middle value is greater than the others, but we need to reach a point where there is such a difference between this observed set compared to our expected set that statistically speaking, it is less likely to be due to chance and more likely to be due to something else. So the whole purpose of the chi-squared test is to be able to compare particular sets. So we'll use this particular sample size, we'll use this idea of 10 to 20 to 10, and we'll use this 10 to 16 to 14 ratio and go, well, how different are they? Okay, do they look different enough to be statistically significant? So let's have a look at the formula that we would use. So fairly straightforward formula. We've come across this sigma sign before, okay? This chi-squared bit over this side, sorry, this is what we mean by chi-squared. Big error that many students make at A-level and at university for that matter is they see that figure that says chi-squared, and this is chi-squared. You never have to square root anything to get to chi on its own. It's called the chi-squared test, and we are working out what is chi-squared. Okay, so there's no square root calculation in this at all. That's what many students often feel they need to do. So don't be tempted to go down the route of, pardon the pun, go down the route of doing a square root to get chi on its own. It is the chi-squared test. Then we have is equal to the sum of, the sigma symbol, we've looked at that before, is the sum of the O and the E are observed and expected. And so if we know observed and we know expected, we can kind of start putting those into this particular equation to work out our chi-squared. And the whole purpose of this test is to look at the differences between our observed and expected that is predicted by our null hypothesis. So the null hypothesis for chi-squared is pretty straightforward. There is no significant difference between the observed and expected frequencies. Okay, so this is you can do alternatives to that, but this is a fairly standard way of assigning a null hypothesis to any chi-squared statistical test. There's no significant difference between the observed and expected. So let's go through the example and see how it works. So this is the standard kind of table that you're worthwhile generating to come up with our chi-squared value. So keep the headings nice and simple. So in this case, we've got 3 different categories because we're looking at particular genotypes. So we've got homozygous dominant at the top up here. We've got heterozygous and homozygous recessive. So we've got 3 different combinations. We then have our observed results, 10, 16, and 14. And when we looked at our sample size of 40, we had a 1 to 2 to 1 ratio. We determined what our expected results would be. Okay, in this case, 10 to 20 to 10. So what I want you to do now, I want you to pause the screen and I just sketch down this particular table, and I'd like you to see, can you work out the values that are missing from this table at the moment. Okay, so the first column that's missing is observed minus expected. So observed minus expected, it's going to give a value in here. Then we're going to square that value. That will help deal with any negative values that we've generated. And we're going to take that value that we've generated and divide that by our expected. That's going to give us 3 numbers in this final column, and to get to chi-squared, we simply add those 3 numbers together. So fairly straightforward. So if we pause the screen now, can you work out the missing values? Okay, so as we go through, O minus C for the top column, 10 minus 10, simply 0. 16 minus 20, don't forget to include the negative value, so it's minus 4 and negative 4. 14 minus 10, plus 4. We then have observed minus expected square. So we're going to take that value and square the value. So 0, 4 fours, 16. Got rid of that negative value, so it's positive 16. And we've got 4 here, that's also 16. Then going to divide those by E, by our expected value. 0 again. So 16 divided by 20 gives us 0.8, and we've got 16 divided by 10 gives us 1.6. So the chi-squared value is quite simply the sum of those 3 values that we've determined. If there were more categories, it would be the sum of all the values that you have generated in that final column. That gives us our chi-squared value. So if we add those together, for this particular investigation that we're looking at, we have a chi-squared value of 2.4. Now, as with previous statistical tests that we've looked at, we then take that number and we're going to compare it to a set of pre-calculated or predetermined statistical values using what we call a lookup table. And as previously, we had to have what was under our degrees of freedom that we looked at when we did the student t-test. So if you can't remember what degrees of freedom are, go back through the student t-test presentation and just remind yourself of that idea. But we need to have degrees of freedom. And in this case, the degrees of freedom is quite simply the number of categories minus 1. It's exactly the same as we had with the t-test. T-test, we had 2 sample sizes, so it was 1 less for each sample size. In this case, we've got 1 set of values down here. We've got 3 possible categories. So it's the number of categories, in this case 3, minus 1. So for this particular investigation, our degrees of freedom is 2. So we now have 2 values. We have 2 degrees of freedom and our calculated test statistic 2.4. So what we do now is we compare our value to the value in a lookup table. So here's a lookup table. We're looking at our degrees of freedom. We can see number 2. So we're looking at this row. And we've got different levels of probability. We're looking at the 5% level. So it's this highlighted column here. And so the value that we're interested in comparing our test statistic to is 5.99. So we got a value of 2.4 and we're comparing our value to that 5.99. This step here is very, very similar to ones you've seen before. We do exactly the same process yet again as we did with Spearman's rank and when we did the student t-test. We're looking to make a decision, is the value that we have calculated, is it greater than or equal to the value in the table? So in this case, it isn't. The chi-squared value we determined, 2.4, is less than the critical value. It's less than 5.99. And thus in that case, we accept the null hypothesis. There is no significant difference between the observed and expected results. Okay, so what we would need to finish that off with in terms of our interpretation, there is a greater than 5% probability that the differences between the observed and expected frequencies were due to chance. So we're saying, yes, there was a difference, but it's highly likely that actually the difference that we got was just simply a chance event. Okay, so let's just recap on the steps involved. Let's kind of just go through every little step and let's think about what we had to do. So first thing we would do, collect the data from the real situation. In this case, we're looking at genetics cross, but it could be from anything. So you'd collect your data that you've got in the field, okay, whatever that might be. You then work out your expected results. That's usually the most challenging step. Okay, for genetics crosses, it's invariably the ratio of whatever you were looking at. And quite often the expected results is often the mean value across a number of categories or an even distribution of a particular value across the number of categories. But once you've done a couple of examples, you'll see where that expected result comes from. You then look at the difference between the two, square the difference, divide by the expected result, add them all up, and then compare it to a value in a lookup table like this one. And once you've done that, you can then decide, are you going to accept or reject your null hypothesis. In terms of degrees of freedom, it's the number of categories minus 1. And if we end up with a probability above 0.05, okay, we're saying there's no difference. But if we can get a probability below 0.05, okay, so 0.05 is our significant difference value, so you can get down to 0.01 and 0.001 and so on. We're interested in that 5% level. So anything less than 5%, we're saying, look, there is a significant difference between those two samples that we've got, our observed and expected, so it's likely that something has influenced the outcome. So as a recap, just to think about the interpretation phrases, this is what we need to have. If our calculated value of chi-squared is lower than the critical value, there is a greater than 5% probability that the differences in observed frequencies and expected are due to chance. We would accept our null hypothesis. And if our calculated value of chi-squared is greater than or equal to the critical value, there is a less than 5% probability, so less than 5 times out of 100 would the differences in observed frequencies and expected frequencies be due to chance. In that case, we reject our null hypothesis. So if you look at those two phrases there, you can see huge similarity between the phrases that we looked at for Spearman's rank and the phrase that we looked at for the student t-test. So these particular examples that you need to kind of commit to memory. So when you do any particular statistical analysis, you're kind of drawing on this kind of basic principle of how to interpret the particular result for those tests. Okay, I've set you some examples to work through, so look back at this one again, go through the steps, just reinforce what we've done. There's 2 more worked examples to you to kind of work your way through. And then there's a number of questions that you can tackle, and I'll supply the answers to those in due course. So any problems, as I said before, drop me an email and hopefully you'll have success at doing the final statistical test, chi-squared. Good luck, and I'll speak to you again soon. Bye for now.